Okay. I think that did it. Let me just double check. Perfect. All right. All right. So we have voluntary and involuntary movements. You know, we have our reflexes. It's not really voluntary. Hiccups or twitch aren't really things that we choose to do, but we do them before thinking. Our acts, so it's things that we actually decide to do. You know, movement, writing our name, playing guitar. But either way, we do get a motor plan, and our areas in our brain, specifically in the frontal cortex, is going to be setting commands and providing actions, whether we choose to do them or not. Yeah. So the really important parts here is our primary motor cortex and our basal ganglia and our cerebellum. Um, we remember that our precentral gyrus is going to be our primary motor cortex. We are also going to have our prefront. Oops. We're going to also have okay, I guess I can't have different colors. What's up with that? All right. So we have also our prefrontal cortex, which is going to be the planning of that motion, but the primary is going to be the actual execution area that's going to talk with our basal ganglia, that is going to make those decisions. And then once we need to make our fine motor movement, it'll go to our cerebellum and we'll make that action happen. So we have our skeletal system that's going to hold our muscles, and it's going to be making our movement happen. And then our spinal cord, which is going to be the direct activation of muscles that is going to be caused by our brain sending that information to the spinal cord to the muscles. And so we have our primary motor cortex and non-primary. So primary is going to actually be doing the initiation, while the non-primary is going to be processing and kind of making and planning. And the cerebellum, basal ganglia, is going to kind of process, make fine detail, turn certain muscles on, certain muscles off, so that we can make the action we planned on. So input to output, all of our planned movement or even unplanned movement are because of the world around us. Either we see something and we're going to respond to it, we feel something and we respond to it. Sometimes when we feel something, we might respond to it as a reflex, and usually when we see something, on our normal day-to-day, it is from a plan, unless something's, coming at us and we want to respond right away. But in this image, we are looking at, say an elevator, we want to go up, so we're going to hit that green button. So as we see it, that comes into our eyes, lateral nucleus, occipital lobe, and from the occipital lobe, we start to make our differentiation on where something is, what something is, and we're going to make our plan for that in our prefrontal cortex. That's going to be sent to our premotor cortex and our primary motor cortex. And once we decide, all right, we need to move our finger, our arm, we need to step towards this, all that information is going to be given down to the spinal cord, and we're going to cause that to be an action. In our spinal cord, we have our motor neurons, and these are going to be the axons, or neurons that are actually going to go directly to the nerve, is going to be the nerve that's going to go directly to the muscle to activate it, to either relax it or tense it, extend and contract, so that we can perform our action. So it's going to be a regular action potential that travels down this neuron and is going to branch into these muscle fibers. Notice that when a neuron is activating a muscle, that is the neuromuscular junction, so it's neuron directly onto that muscle. And that is coming from our ventral horn. So remember that we get our sensory from our dorsal horn, from that dorsal root ganglion, but when we talk about motor, it's going to be coming from that ventral horn. So the neurotransmitter that is released in that neuromuscular junction is acetylcholine. It'll always be so. Nothing more specific on that. There's quite a lot of detail in this image, but really the important side of this is the fact that acetylcholine is that primary neurotransmitter. The motor endplate is that part of the muscle that receives the information from that neuron. So the neuromuscular junction is the synapse of the terminal buttons to the motor endplate of the muscle, which is going to lead to the activation of the fiber in the muscles. And that is the final common pathway, basically meaning that you know that neuron is the last order neuron of this process. Now, when we move, our muscles work in tandem or oppositely so that we can make a motion. When we want to extend or flex our arm, we have our bicep and our tricep, and they are going to be antagonists, meaning that they do the opposite of each other. One of them is going to flex, which is that bicep. So when we flex our bicep, that is going to be coming to our wrist is going to be coming to us. But when we extend our arm, our tricep on the back of the arm is going to be tightened, and basically one of them has to relax so that the other one can act, so that you can't tighten both of them. Your arm won't, essentially yes you can, but your arm won't go anywhere. One of them has to relax while the other one is tightening so that you can get motion in the body, or else they're going to stalemate. So muscles can also act together and be synergists. So we have a lot of small muscles within our body as well that kind of work together. The bicep and tricep are obviously our major muscles that are going to do the majority of that work, but we do also have some tiny muscles that are going to kind of do a little more fine detail within their movements. Say we want a specific type of rotation that's going to work together to do that. So here we also talk about a tremor. So something as if someone was to have Parkinson's disease, they kind of have that shake, tremor. Or also there are also some other diseases that cause this as well. And that is basically they're going to be an issue within the brain, or what can also be an issue of the balancing of these antagonist muscles. usually normal when someone is at rest, they're not really moving at all. Those two muscles are balanced. They're either equally tight or equally relaxed. But when you have an imbalance on those muscles, you can get a tremor. So within the muscle fiber, we have these myosin and actin, and what happens here is that when we get our acetylcholine from our neuron to activate our muscle fiber, the actin is going to stay in place while the myosin is going to make a movement. And what happens is that these head pieces of the myosin are going to bend and grab onto the axon, and kind of it's going to come grab and pull the actin, and that's going to cause tightening of the muscle. This is happening, maybe even a million times down one muscle fiber, but this is how it works, is that there's tons of these, I think what they're called Z units, that whenever acetylcholine comes in, we're going to have this bending and grabbing and kind of pulling of the actin so that we can have contraction. Notice that actin is also found in the cells. It is one of the cytoskeleton. So know that actin is kind of a structural component to this area, as well as it is a structural component to a cell. And the myosin is the part that's going to be moving and manipulating that structural component. So when you move the structure and bring it all close together, you're tightening it and causing that contraction. So the full entire motor unit is going to be one neuron that is activating the however many number of muscle fibers. So in this diagram, the motor unit is one neuron and 3 muscle fibers, though usually you have kind of a ratio of 1 to 13, but you can also have some more fine um, neurons that are going to do a little less so that you can have very fine movement. The less that you have, the smaller a movement you can make and more precise. If one neuron, innervated, say 1,000, then one neuron is going to have a huge movement, and it's going to cause a very, not random, but too big of a movement. You won't really have precise movement. So something where it would be like, your handwriting, you wouldn't really be able to write small, fine detail, really draw a nice picture. It would have to be very large things because you'd have to have only big movements. So just notice that, or remember that the motor unit, one neuron to however many fibers its axon ends up innervating. So we have our upper motor neurons and our lower motor neurons. That lower motor neuron is going to be what is going to lead to the motor unit. So we see that we get a neuron up here, and we have another neuron down at the motor unit. We have direct control with the lower motor neuron, and we have indirect control with the upper motor neuron. This means that our brain at the upper motor neuron can make a decision, and it will then go and tell someone or the lower motor neuron to do it. It has indirect control because just because the brain told it to happen doesn't mean it's going to happen, because the lower motor neuron is really the one that's going to make it happen. So this is the direct control. If the lower motor neuron is damaged, then it won't matter what the upper motor neuron said, because it doesn't have direct control. Only the lower motor neuron does, and thus has direct control. So there are two types, being alpha motor neurons and gamma motor neurons. These will be the lower motor neurons that are either alpha, so it's number one, primary, it's going to actually be making that movement, while gamma is going to be intrafusal fibers that are going to kind of be sensing the movement, and is going to add a stretch reflex, and it's more reflexive as opposed to a voluntary movement like the alpha motor neuron. So these gamma motor neurons are inside these muscle spindles. So they're called intrafusal because they're inside fibers. They sense and respond to the stretching of muscles, and they can kind of tell where things are, which is what proprioception is. It tells you where your body is in your environment. So if you have your arms stretched out, but you have your eyes closed, you still know that your arms are stretched out, and you can kind of move your arms around with your eyes closed, but still know where your arms and legs are. That's because we're still getting this information. We're feeling that we are either stretching or we're tensing our muscles. And that's what these gamma motor neurons are doing. It is responding to that reflex, and the proprioception is going to be a sensory response that we get from our muscles. This also leads to our stretch reflex circuit, meaning that when, say, a weight gets dropped into your hands, you don't have to, your brain doesn't have to necessarily process that information, because if it did, it would kind of take a long time to respond to it. And I kind of like the example of when you're walking upstairs and you kind of don't lift your leg up high enough, and you kind of kick that step, and you're kind of already kind of moving forward, so your momentum is pushing you forward, and you miss that step. So you're about to fall over, but you immediately lift your leg up higher and kind of stomp down, so that you can kind of catch yourself. I do this all the time. I kind of just don't lift my legs up high enough. But you correct that mistake really quickly, and you almost exaggerate the next step, so that you, in a way, lift higher and stomp down harder than you normally would when you're climbing upstairs, because it's in a reflex action. The information that I kicked the step came into my leg. I know my body immediately notices that my balance is falling forward and that I shouldn't be, and so that information comes into my spine through our sensory dorsal root ganglion, and just immediately tells my the muscles that it needs to correct that response, and so it doesn't even tell my brain before it just goes ahead and makes that action to correct it. So this is why we have reflexes that you kind of think to yourself, oh wait, why did I do that? Because you acted without thinking. And that's because we have this muscle mechanism that when something that we don't expect happens, but we need to act immediately, or we're about to lose our balance, we have a correction mechanism with our reflexes. And here's our upper motor neurons, where we have our indirect control. We're getting our information from that primary motor cortex. It is being sent down to our spinal cord and is going to be sent to our medulla. It is going to cross over and keep going down. So in a way, this mimics our touch pathway, where we have our cross at the medulla, our decussation at the medulla. The name for this pathway is our cortical spinal tract, or some say the pyramidal tract. It's called pyramidal because it's the special kind of cell that is used for our motor pathway, but cortical spinal is usually what it's called. So cortical means the cortex, and spine means spine. So we're getting information from our prefrontal cortex, and it's sent down to our spine, sent down to our body, and we get motor action. So the basal ganglia is going to decide what major muscles are going to be either on or off, relaxed or activated for these movements. And she does list a few portions of the basal ganglia, but doesn't really tell you what they do. So I would assume, yes, you have to know what those three parts are, as well as these additional parts. But the three main parts are the caudate nucleus, the putamen, and the globus pallidus, and then some kind of like secondary parts that aren't really attached to the basal ganglia but are still considered a part of that is the substantia nigra and the subthalamic nucleus. Essentially, it's going to be making that big decision of, all right, this big muscle group is going to be making this action. Then we are also going to talk with our cerebellum, where our cerebellum is almost like a small, its own brain in itself. It is full of little gyri. It has lots of surface area. It contains a lot of information, and it really focuses on that fine movement of our body. And essentially, what it's going to do is going to give the information on, all right, which motor units do I have to activate? So the basal ganglia is going to be like, all right, which giant muscle do I have to activate? And the cerebellum is going to be which motor unit. So it's going to be very fine. It's going to be, all right, just this neuron or just these few neurons have to activate so that we can make this action happen. And when we learn to ride a bike or we learn to read or to write, it is really our cerebellum that is causing these actions because it does the understanding of these little few muscle fibers are the ones that need to be activated so that this action can happen.
Yeah, the cerebellum plays a role in motor learning, and it also plays a role in like course correcting. So in the middle of a movement, your cerebellum is always monitoring like what you're doing and how you're doing it. And the reason you're able to achieve that specificity is because it's always course correcting in the meantime, whereas the basal ganglia is more involved with initiating movement.
So here we see this topographic map of our brain again. Remember that we saw this with the sensory cortex that we have our legs up top and then our head down on the side of the brain. So just as we can feel this in our primary sensory cortex, we also in our primary motor cortex, when we want to initiate movement, we also have these specifically defined areas where each part of your body is differentiated so that we can make movements based on those parts of our bodies. So that's the primary motor cortex, and then we have our non-primary. So we have our supplemental cortex, and we have our premotor cortex. So the supplementary is going to be sequence of movements, kind of thinking, all right, I'm going to make 5 steps forward, turn left, make a few steps that way, and that's going to bring me to where I need to go. So it's kind of that sequential, we're going to do this, and then we're going to do that, and then we're going to do that. And the premotor cortex is going to, neurons activated when the motor sequences are guided by events, and they fire pretty much just before acting on the activity. So we have this plan, we're going to start having these sequence of movements we want to do, and then right before we're starting to do them, the premotor cortex kind of just runs through the game plan real fast and starts to do it right before we're doing it, so that when we execute it, we had an initial run through, basically. This is a mouse's brain, so I can't really tell you where this is in the human's brain, but we also have these mirror neurons that are in the premotor cortex, and they're basically our monkey see, monkey do neurons. We are able to watch someone do something and kind of already in our mind play out how we would do it, and we can essentially mimic somebody just by watching them, as opposed to having them have to move our limbs for us so that we can make the same movement. We're able to, within our mind, kind of pre-fire and kind of have an idea of how to make that movement. And we use this, especially if you're into sports or maybe into dancing, when you see someone do a really cool dance move, or you see someone do a really they outplay somebody in a sport, and you want to do that later. You're able to see it, understand what muscles they're moving, and you'll be able to visualize yourself doing that action so that you can later do that yourself. So again, the cerebellum and basal ganglia modulate our movements. They are going to be in the early phases of the movement, and then the primary and spinal cord are going to be in the later stages on finally making our actions. Do know, which ones are acting first. These time graphs are going to be helpful for that, saying that the primary motor cortex is first. We're going to then talk to our basal ganglia and cause that planning and initiation, and then move to our supplementary motor area and cerebellum. And then finally, once all that's decided, go back to the motor cortex and make that happen. So here's another review on those two things. Again, I'll just send the slides to the group so that you guys can have these. Now we have a couple disorders or disruptions in movement. know the definition of ataxia. So that's our loss of coordination. Imagine like taxi, you're moving, you're going from one place to another. So when you have ataxia, you're unable to make those movements. You're unable to get yourself from one place to another. That might not be just no movement, but it could just be like the disruption of movement, broken or segmented movement. So it can be almost like someone's doing the robot dance, where they're just doing small individual movements as opposed to being very fluid. They are very broken and individual movements. And the two main diseases are Parkinson's and Huntington's disease. They're both related to the basal ganglia. So for Parkinson's, it's specifically substantia nigra. She will very likely test on both of these diseases because they are pretty important. So know them as best as you can. Pretty much that this might just be one of those memorization steps, because from this information directly, they are different enough from each other that you should be able to remember them separately, and they don't go into far too much detail. Any questions or anything, Divya, that you want to add to this?
Nope. No, that's about it. We just have to go over balance, taste, and smell now.
Do you still have control?
No.
Okay.
Okay. So with taste, we have different taste receptors on our tongue that respond to different chemicals that are dissolved in saliva. And when these dissolved chemicals bind to the different receptors, that's what we perceive as tastes. So different tastes have different receptors. We generally have 5 main tastes: sweet, salty, sour, bitter, and umami. And all areas of the tongue are going to have taste receptors for all of these different tastes. However, there are areas of concentration. For example, bitter, you're going to have a lot of bitter receptors up here. Sour and salty will be along the sides, and the sweet receptors will be concentrated in the tip of your tongue. So the way these gustatory receptors are set up is that gustatory receptors are tiny cells, individual cells that bind to these chemicals and send action potentials to the brain about it. And they're organized in these little taste buds, and these little pockets called taste buds. And these pockets have these gustatory cells in them, and then little stereocilia that come out of them. It'll be over here. And these taste buds align these structures called papillae on the tongue. And these papillae are the bumps that you see on your tongue. And that's kind of how it is set up. So you have a bunch of gustatory receptors that make up one taste bud, a bunch of taste buds that line up one papilla, and then all the papilla cover the surface of your tongue to detect these chemicals. And these signals are ultimately transduced through the tongue, the brainstem nuclei, the thalamus, and then the somatosensory cortex. And depending on which axons exactly, or which receptors exactly are activated, because remember we have different receptors for different tastes. So depending on which one is activated, that's how the brain can tell which taste or which chemical is on your tongue. So we're going to go through each receptor. So for the receptors that pick up salt or a salty taste, they have sodium ion channels and TRPV1 channels, which detect other salts other than sodium, and it also increases the sensitivity to sodium. For sour, you're going to have proton ion channels that open up and open up when protons are like hydrogen atoms are present. For sweet, sweet, bitter, and umami are GCPR receptors. So salt and sour are just going to be ion channels because they're picking up ions. Sweet, bitter, and umami pick up molecules that are larger than sodium and protons, so they use GCPR receptors instead for these. So with sweet, you're going to have a heterodimer that utilizes T1R2 and T1R3 proteins. For bitter, you're going to have a similar one, a heterodimer of T2R receptors. And with umami, you're going to have a T1R1 and T1R3 receptor. With umami, they respond to amino acids and glutamate, or MSG. And that's what gives you that meaty flavor for some foods that you eat. Okay, so smell works through olfactory receptors. These olfactory neurons line the top of your nasal cavity, and they kind of look like this. These long neurons that poke through the bone, this bone called the cribriform plate, and they have stereocilia that extend beyond. And what happens is the chemicals in the air come in contact with these cilia, and when that happens, those cilia will send action potentials through the neurons up to the brain. And like taste receptors, there's different kinds of olfactory receptors that respond to a wide variation or a wide range of chemicals in the air. And depending on which ones are stimulated, that's how the brain knows what chemicals are there and what smell you're smelling. So here is kind of how they're organized. You have the different colors of receptors represent like the different types of olfactory receptor cells that pick up different chemicals. And each type of olfactory receptor will send its axons to a specific glomeruli. And each glomerulus kind of organizes all the receptors for one specific smell in one place and projects those axons to one mesial cell, which will then send it down through the olfactory bulb and to the brain. And this organization kind of allows the brain to distinguish which chemical is present and what smell you're smelling. The last thing that your brain does have, or the nervous system plays a role in, is balance. So the brain picks up on balance through the use of the semicircular canals and these other organs, the autolytic organs called the utricle and saccule. Together, they're called the vestibular system, and they're in your ear, right next to the cochlea. And how it works is that there are these three semicircular canals that are filled with fluid, And at the end of each of these canals, there's this kind of enlargement called the ampulla. And inside the ampulla, there are going to be these hairs or these stereocilia that are inside. And depending on which way you move your head, the fluid inside them will move, and it'll move, the movement of the fluid is going to move the stereocilia, and that's what's going to cause. And then when those stereocilia are moved, they're going to generate an action potential and signal to the brain that your position of your head has changed. And these semicircular canals detect rotations in the X, Y, and Z axes. These are rotations of your head, whether you're shaking it left or right, or tilting it, or yeah. In contrast to just rotating your head, the utricle and saccule actually pick up on horizontal and vertical acceleration. These are two other organs that are similar to the semicircular canals. They use a different method of picking up these movements. Instead of using stereocilia, they have these things called otoliths. And depending on whether your head is moving forward or backward or up and down, they will pick up on that movement. Okay, yeah. And the vestibular and those neurons and the utricle and saccula will transmit that information through the vestibulocochlear nerve to transmit that information to the brain on position. Do any of you have any questions about that or anything we talked about? Okay, well, if you guys don't have any questions, then that is it for now.
Please feel free to DM us on GroupMe if there are any follow-up questions. And I will soon get this onto YouTube, however long it takes for it to show up on there. All right, everybody, good luck on your studies. And yes, I will also get the PowerPoints together for y'all. You're very welcome. All right, take care, good luck, do your best.